Let's talk about how we figure out what molecular structure looks like in 3 dimensions. In order to tell how simple molecules look in 3 dimensional space, we can use a simple theory called the VSEPR model or VSEPR theory. And again, the point of this is to tell molecular structure, which is just how atoms in molecules are arranged in 3 dimensional space. Um, the VSEPR acronym stands for valence shell electron pair repulsion theory. And it's based on a very simple principle that electrons, being negatively charged, repel each other. And since they repel each other, they want to be as far apart from each other as they can be in 3 dimensional space. This applies whether those electrons are involved in bonds or whether they are in lone pairs, non-bonding electrons. So I have given you a handout on how to determine molecular geometries by VSEPR theory. It's a 2-page handout with a front and a back. And this handout summarizes the information in section 4-1 of your book. They have very similar tables, and what this handout does is it essentially condenses all of the information in the book's tables into one simple handout. So, the concept behind VSEPR theory, or valence shell electron pair repulsion theory, as I said, is that electron pairs repel one another. And this applies to electrons that are involved in bonds and electrons that are non-bonding, electrons that are in lone pairs. Because of that repulsion, they want to get as far apart from each other as possible in 3 dimensional space. And that determination to get far apart from each other is what determines the 3 dimensional shape of molecules. So, how do you figure out what molecular geometry should look like for a given molecule? It's pretty simple if you follow these steps. The first step is to draw the Lewis dot structure of the molecule. And when I say draw the Lewis dot structure, we've spent a lot of time drawing Lewis dot structures. You want to draw the best possible Lewis dot structure that you can for it using the rules, using the handy hints that I gave you for drawing Lewis dot structures. Then you want to arrange the electron pairs to minimize repulsion in 3 dimensional space. And in order to do that, there's a simple trick. You count up the total number of single bonding electron pairs and the total number of lone pairs around the central atom only. Okay, so you're looking at the central atom and you're counting up the total number of single bonding pairs and lone pairs. That number, whatever it is called the substituent number. So when I tell you to do that, it's pretty simple. One thing that you should always be aware of when you're determining the substituent number is that you don't count multiple bonds as multiple substituents. That's very important. That's really the only trick to it. So a doubled bond or a triple bond counts the same as a single bond. So if you are looking at, for example, let's take carbon dioxide. And you want to figure out what the substituent number is on the central atom, which is carbon. So SN stands for substituent number. You're looking for the regions of electron density around that central atom. So you would just count that and that, each of those double bonds as 1. So the substituent number here is 2. So the double bond just counts, each double bond counts as 1 in the substituent number count, 1 region of electron density. So that would be similar for, let's say we have BEF2. Here's the Lewis dot structure for that one. And we want to figure out what the substituent number is on that central beryllium atom. So in that case, we're just looking at single bonds, but it's the same. Each single bond counts as 1 region of electron density. So the substituent number here would be 2, just like it is for carbon dioxide. Now, each lone pair also counts as one. So if I'm looking at, say, water, which everybody knows is H2O, here's the Lewis structure for water, and I want to figure out what the substituent number is around that oxygen atom. Each bonding pair of electrons counts as one, 1, 2, and then each lone pair counts as 1, 3, 4. So the substituent number here would be 4. Now let me give you a similar example. Let me give you NH3. This is the Lewis structure for ammonia. And we want to figure out the substituent number around that nitrogen atom. So we count each lone pair and each bond as 1. 1, 2, 3, 4. We get a substituent number of 4 around that nitrogen. And finally, sometimes you have a mix of things. Let's take the carbonate anion, for instance. So here is a Lewis structure for the carbonate anion. It's got formal charges on it. And those formal charges give rise to an overall charge of 2- on the ion. Let's say we want to figure out the substituent number on that central carbon atom. So we would count up each bond, be it double or triple, as 1. So 1, 2, 3. We get a substituent number of 3 around that central carbon. So that's how you count up substituent numbers. You never want to count multiple bonds as multiple substituents. Just any bond, regardless of whether it's single, double, or triple, counts as one region of electron density. And each lone pair counts as one region of electron density. So that is how you count up the substituent number. Then once you have the substituent number, you choose the geometry corresponding to the substituent number from the table on the back of this handout. And that is what I will describe in the next lecture.